Good morning, good day, good evening. Welcome to this presentation on the benefits of 3D in plant simulation. My name is Mark Philip Hermans. I was born and grew up in Belgium. I studied at the Maritime Academy Antwerp. I work for Audi Hungary as a manufacturing engineer specialized in discrete event simulation. Our agenda. First of all, I would like to start with an explanation why I started using 3D. Secondly, I will share some beliefs I had myself and still see with a lot of my colleagues. Thirdly, I will give a short introduction to self-animation and poses in plant simulation. Knowledge needed to understand the next topic, benefits of the use of 3D in plant simulation. And last but not least, a short summary. With the rise of freely moving AGVs, the overall realization time for standard production lines sincerely reduced. Not only ways had to be found to reduce the overall simulation project time, but also ways to bring the model appearance, feel and controls nearer to reality. Moreover, electrifying our products confronted us with new challenges, where half-finished products and product carriers had to return to the same resources several times over. To keep track of these intertwined transports, the copying of these levels from reality into virtual reality became simply obligatory. It became quickly obvious that things like not only length, width, height, but also distance, shades, and working levels all have an influence on the material flow and the evaluation of these flows' behaviors. The feeling of a model should match feelings reached by Don Eddy in his painting Green Volkswagen. Photorealism is very important. Based on shades, forms and proportions, one easily gets a feeling of the task, speed and the influence of the AGVs on the material flow. Incorrect shades or proportions will lower the acceptance of the results. In this example, I needed to explain the build-up of products on the bridge between two production loops. Finding the bridge and defining the height of the several lifts used, I had to use the 3D layout files. 2D information was insufficient to build a proper model. During the modeling phase, using standard objects, I rebuilt the conveyor system, including several lifts based on the layout in 3D. To make a proper control of positions, heights, and so on, I simply copied the 3D layout into a deco layer within plant simulation, generating a fast visible control for all conveying elements and as a spin-off producing a real management teaser. One of the biggest reasons not to try new and unknown functionality is our fear for the steep learning curve. Reality, on the other hand, shows often that not the learning of these features takes a lot of time, but that most of the time the needed information is missing and has to be collected or generated. Once our first model is ready and halfway functioning, after hours or days of trial and error, you yourself will get a feeling that the whole thing is only about beauty and useless animation. And if you present your model to your good colleagues, they probably will start stumbling over facts like workers running through each other and parts entering through closed doors. At the end of the project, your team, including yourself, will find your fancy model very time-consuming, misleading, and with little added value. But wait, let us have a look on how to manage self-animations and poses with the object of correcting this idea. Self-animation I use to model movement within an object during machining. An example can be the turning or rotating of the part or some tool movement. Poses I basically use to model internal transports and logistics. An example can be a swiveling table by which a part change is done within the machine. Not only the dialogues are almost identical, but also the built-in methods are comparable. In this sense, mastering one means mastering both. The most important functions are functions for playing, pausing, restarting or unpausing, and resetting the defined animations. Probably the most important function is the one for getting the total remaining animation time. This function can be called at any time during the animation and returns the remaining portion of the animation time. Creating a self-animation is done in the following steps. Optional, the creation of one or more animatable objects. Secondly, define the paths to be used. Defining the anchor points with start and stop positions, eventually with time. And of course, building an overall control to select and activate the animations according certain events. Creating poses is done in the following way. Obligatory, creating an animatable object or objects, defining the joint and joint types on these new created objects. On the main object or frame, defining the poses, defining the active joints, their endpoints, and the time to reach them. And last but not least, the overall control. On the next two slides, I want to give a short example on the overall control for self-animation. Poses is done in a similar way. On this slide, you see the part of the control in case the animation is active. The play function at call returns the duration of the scheduled animation run. During the animation run, with the use of a loop and the wait until or stop until function, an observing method is created. This method reacts to any change of the point operational parameter. For example, at failure start, the loop will suspend the animation run, and at return to operational state, the remaining duration is sampled and the animation run is continued. On this slide, you see the part of the control in case the animation is not active. The structure is absolutely the same. The difference is that the duration between the beginning and the end of the movement must be calculated or selected from a list or table. In case of, for example, failure, the extension of the animation period is calculated over timestamps at the beginning and the end of the failure. The difference between the calculated animation time and the delta between the two timestamps gives us, in this case, the remaining animation time. Main benefits of the use of 3D are a search and model value, faster project approval and acceptance, and a sincere performance boost. You will have a search and model value for your customer because it is nearer to reality. For your specialist because he has much better control structures which easily can be reused and adapted to other objects. For your stakeholders because you can offer them an extreme realistic teaser on the planned line. For your documentation team because a lot of 3D is self-explaining. You will have faster project approval and acceptance because opposite to 2D, which needs clear descriptions and design information, 3D is almost self-explaining. Moreover, using Edison, you will get the possibility to get interactive with your customer, speeding up the acceptance even more. You get a real performance boost because the animation is shifted to the GPU and the amount of simultaneous events is extremely reduced. This performance boost will reduce the machine time needed for experiments. Enough talk. As example, I bring you a model using a so-called star buffer. The original model was 7 years old and built in plant 10.1. Last year, we wanted to use the model to make some evaluation on the integration of a few new products. I used this occasion for an upgrade to get all objects into 3D. On the left, you see the model of this star buffer in the original model. On the right, the same buffer in 3D. The 3D model gives a much better feeling of the proportions of this machine. The 2D model needs a lot of explaining, and without documentation, changes are as good as impossible. Functions of the conveyors and the carriers used are absolutely not self-explaining, meaning you have to sit down with your customer, take a drawing of the machine, and spin your web of definitions to give your customer some understanding of the model. The 3D model is almost self-explaining. The conveyors with each 6 containers are replaced by 2 parallel stations, each dimension 6 by 1. Moreover, a breakthrough, as seen on the upper disk, can easily be defined and handled over poses. In the 2D model, this was done by a combination of sensors and change in distance between the used containers. Still, the conveyor modeling the upper disk had no breakthrough. The control structure of the 2D model contains at least 8 controls with 445 lines of code, 2 lists and 2 tables for material handling. Moreover, because the disks are modeled as conveyors, all calculations needed for moving the containers are also active during calculation without animation. The 3D model has 3 controls with 240 lines of code and 4 global variables, 3 strings and 1 integer. These variables are not only at the heart of the control, but give an easy way of creating statistics for the object by using the variable internal statistics collector. Moreover, because this model uses an equal control structure as described earlier, all movements are deactivated if the animation is inactive and reduced to simple waiting and sleep instructions. In case of performance, the 3D model well outperforms the 2D model. With animation, the 3D model is as performant as the 2D model. Without animation, the 3D model is almost factor 3 faster as the 2D model. Reasons mentioned are the use of the GPU for the animation and an extreme reduction of simultaneous events through the use of poses. With no extra efforts and no loss of time, a 3D material flow can be created which is damn good looking, extremely performant, really helps your customer in understanding their system, and helps your customer in optimizing efficiently their plant material flows. In our quest to reduce the overall project time span, we focused on the 3D functions and the layers available in plant simulation. Although we also questioned eventual gains, we could produce the following positive results. The overall time span could be reduced by 15%. Main reasons were faster overall project acceptance, less documentation, the reduction of computing time for experiments. Thank you for your attention.